Jackson. It's now time to turn our attention to some real-world applications. And really, this is kind of the heart of what a study of introductory study of calculus, survey of calculus, or Calculus 1 is really all about. We want to try to be able to take these concepts and ideas and skills that we've developed and apply them to real-world situations. Now, some of this we've done a little bit before in our basic interpretation of the derivative chapter or unit or playlist. But let's take what we already know about the meaning of the first and second derivatives to provide some information relating to real-world situations. Now, what we want to do in these situations is we want to be sure that we respond in terms of the context of the situation. Now, this first set of problems that we're going to look at here make use of interpreting the derivative as a rate of change. Remember, it is an instantaneous rate of change. Also remember that the units of the derivative are the units of the output variable divided by the units of the input variable. So they're always fractional units. And that alone can help you interpret a lot of times what is meant by the derivative. Remember, we're asking about the sign of the derivative. In other words, whether it's positive, negative, or zero on the derivative is equivalent to asking about the direction of the original function, whether it's increasing, decreasing, or constant. Also, remember the local linearity property of the derivative. So the derivative is approximately the amount of change in the function when the input is increased by 1 unit. Actually, when you increase the input by 1 unit, the derivative is the amount of change on the tangent line. But that's very close to the amount of change in the function because the tangent line is close to the function if you're close to that point of tangency. That's the local linearity property. So, as usual with these videos, what I'd like to do is present some problems for you and have you work out solutions and then come back and check your answers. And so I'll ask you to press pause at various places and then go on. We'll work a few examples in this video, and eventually I'll have up a set of videos over many examples. So here's the first one here. Let h of t be the height in inches of Dr. Jackson, of me, t years after my birth. What are the units of h prime of t, and what can you say about the signs of h prime of 10 and h prime of 30? See if you can work that one out and then come back when you have an answer. Press pause now. Well, if the height is in inches and t is in years, the units of h prime of t, which is, of course, dh over dt, is the units of h over the units of t. So that would be inches per year. So it's a rate of growth. Okay, so h prime of 10 is going to be positive because on my 10th birthday, I was gaining in height. 10-year-olds are growing in height. So that should be a positive sign there, because the original function h is growing at that point. On the other hand, h prime of 30 is probably 0, because on my 30th birthday I was not gaining height or losing height. So the function h, the height, was constant at that point. Okay, let's try another one. Okay. An economist is interested in how the price of a certain commodity affects its sales. Suppose at a certain price of $p, a quantity Q of this commodity is sold. Okay, and if Q is f of p, explain in economic terms what the meaning of the statements f of 10 equals 250,000 and f prime of 10 equals negative 28,000. And why would f prime of 10 be a negative number? Why does that make sense? So see if you can answer those questions. Again, press pause now. Okay, well, let's see what we've got here. Well, this first part here is just pre-calculus. It says f of 10 equals 250. So it says when the input is 10, the output is 250,000. Now, which one's which? Well, F is just another letter for Q. So this should say Q of 10 equals 250,000. So Q is 250,000 when P is 10. So that says when the price is $10 really per item, so that's a unit price, and then we sell 250,000 of those items of that, whatever that commodity is. Okay? Now, the F prime of 10 says that the derivative is negative 28,000 when the price is $10 per item. That's the instantaneous rate of change. Why is that negative? Well, to say that the derivative is negative is to say that the original function f, or q, is decreasing. Remember, you always increase the input variable when you're talking about whether a function is increasing or decreasing, and you see what happens to the output variable. So here, if we increase the input variable, so we increase the price per item, what's going to happen? Are we going to sell more items or fewer items? Well, you know, if the price goes up, you're more likely to sell fewer items. So we should see a drop in sales, which means that the quantity, F, or Q, is a decreasing function of the price, the unit price, P, so the derivative is negative. Now, we can also interpret this a little bit better using our local linearity property. So we're looking at this part right here. So if we were to increase by $1 per item, which is above 10, we should see a decrease in 28,000 items sold. So increasing from $10 to $11 will result in about 28,000 fewer items. More appropriately, if we increase, we can increase a little bit less than that. In fact, the least is probably a cent per item. If we increase the unit price by 1/100th of a dollar, in other words, 1 cent, then what's then how many fewer items? Well, we divided the here's if we go up by $1, we expect about 28,000 fewer. If we go up by 1/100th of a dollar, we go down by 1/100th of this, which is 280. So approximately 280 fewer items are sold. Which of these is better? The better approximation is the one that's a smaller delta x. So this is more accurate to say that we'll be really close to 280 fewer items if you go up by a cent than it is to say that we'll go down by, that's better than saying we're going to go down by 28,000 items when we go up by $1 in price. So again, what is this really? The derivative is negative 28,000. It says if you're going along the tangent line, going up one unit on the input, $1 per item, will make us decrease by 28,000 on the tangent line. So increasing by 1 cent will make the tangent line go down by 280 items. That's exact for the derivative, but the tangent line and the curve are not necessarily the same unless, of course, the curve is actually a linear curve. And so the smaller you can make that delta x, the more accurate this kind of thing will work. Okay, so those are both correct statements, but the one that's a little bit better approximation is the one here. Okay, let's try another one. A company's revenue from car sales, C, measured in thousands of dollars, is a function of advertising expenditure, A, which is also measured in thousands of dollars. Suppose C is some function of A, C equals f of A. What are the units of f prime of x? And what is the statement f prime of 100 equals 1.5 mean? Should the company spend slightly more or less than $100,000 on advertising? Once again, see if you can figure this one out on your own and then come back when you have an answer. Press pause now. Okay, let's see what we got here. I guess probably I should call this A. You know, let's drop all these F's anyway. It's better to use better units here anyway. So I'm just going to go ahead and use C for the output, which is what it really should be. Okay, and A for the input. So what are the units of C prime of A? Well, they're going to be the units of C divided by the units of A. That is, C is thousands of dollars of revenue, and the units of A are thousands of dollars of expenditure. So it's really $1,000 per $1,000, or dollar per dollar. Okay. Now, in one sense, that cancels out completely to no units, but in another sense, it doesn't, because you want to think of these units as approximating delta C's and delta A's. Okay. So, what does this statement mean about the derivative? Now, notice this is about the derivative, not the original function. We always have to be careful whether we're talking about the function, the first derivative, or the second derivative in these problems. So, this says that the input is 100. What is that? $100,000 is spent on car sales. So, at that point, the instantaneous rate of change is $1.5 thousand per $1,000, or just dollar per dollar. So, what does this mean in practical terms? Well, if we increase by $1, okay, well, if we increase by $1,000, okay, then we should see $1.5 $1,000 increase in revenue. Or, in other words, scale it back. If you increase by $1 in advertising expense, you're going to expect to see approximately $1.5 in additional revenue. So think about that. If you spend $1, you can bring in an additional $1.50. Now, assuming that this doesn't increase your cost anywhere else except on advertising, this is going to be a net increase in profit of 50 cents for every dollar that you invest. So you should invest a little bit more on advertising, and it's going to reap benefits. Okay, it's going to increase your profit. Now, what if we have the same setup in the previous problem, but C prime of 100 this time is 0.8? Okay, what's going to happen there? Should they spend slightly more or less on advertising this time? Well, this time, same basic interpretation. Notice this is still positive. Why was it positive in both cases? Up here is positive 1.5 for the derivative. Down here it's positive 0.8. Well, increasing dollars on advertising expenditures should increase your sales. Okay, I mean, it would have to be something that is so horribly turns off people that they would more likely to not buy your product than buy it for this to not be positive, for this to be negative. Okay, and usually even some poor advertising at least gets your name out there. So it might not be very effective, but it should increase your sales. So it should be a positive number. And certainly that's what they hope. The advertisers certainly hope that it's going to be a positive number for the derivative. Okay, but in this case, an additional $1 spent on advertising is only going to gain an additional 80 cents in revenue, which is going to cause the profit to go down by 20 cents. So in this case, spending more on advertising is going to make things worse. In fact, what should they do? They should spend a little less on advertising, save that money, and do something else with it. All right, how about another one here? Suppose that W represents the wind chill of when the velocity of the wind is V. What are the units of W prime of V? And interpret the information provided by w prime of 20 equals negative 0.2 and w of 20 is greater than 0. And let's assume we're in the United States. Okay, that's going to be important for the units. Okay, can you figure that one out? Okay, let's think about what are the units of W and units of V. Now, if you're in the United States, we're going to typically measure the speed of the wind in miles per hour. And we're going to measure wind chill in degrees Fahrenheit. Other parts of the world, we might measure that in the speed of the wind in maybe meters per second or kilometers per hour or something like that. And we might measure the wind chill then in degrees Celsius. Okay, so in the United States, though, W is degrees Fahrenheit, V is miles per hour. So the units of W prime of V are the units of W divided by V. So they're degrees Fahrenheit per mile per hour. So first of all, why should these both be negative, or why should this be negative? And this should say W double prime right here. Let's fix that. Okay, well, first of all, why is this negative? This says that at the point where the speed of the wind is 20 miles per hour, the wind chill is negative 0.2. The rate of change in the wind chill is negative 0.2 degrees Fahrenheit per mile per hour. So the fact that it's negative says that the function W is decreasing. So what does that say? It says as the wind blows faster, the wind chill drops. Now what the wind chill basically is more or less a miserability index. It's basically how you feel and you perceive the temperature, not the actual temperature that's there. So when the wind blows harder, it feels colder. So we perceive that as being colder, and that's what the wind chill is kind of measuring. Okay. Now this one we don't know. So we should know that that's going to be negative for the first derivative. Now this one says that we're assuming that the derivative, the second derivative, is positive. That means the original function is concave up, and the first derivative is increasing. So it's dropping, but it'll be closer to 0, smaller absolute value later on. So it's dropping, but not dropping as fast. Okay. So once again, so the original graph is concave up and decreasing. So it's going to drop. It's decreasing, but at a decreasing rate. So going from 20 to 21 miles per hour drops about 0.2 degrees Fahrenheit. But the wind chill going from 21 to 22 will drop a little less, maybe only 0.1 degrees Fahrenheit. All right, how about this one here? Suppose that G of t represents the gross national product of a country t years from the beginning of, let's say, 1985. Suppose that at a particular time the gross national product is increasing, but the economy is starting to lag. What can you say about the signs of G prime of t and G double prime of t? Press pause now. Okay, so we said that the gross national product, G, is increasing. So since G is increasing, okay, that tells us that G prime is positive. But the economy is starting to lag. So the economy is the rate of growth in the gross domestic product or gross national product. And so what that means is it's increasing at a slower rate than in the past. So that means that the function is G is increasing but a decreasing rate. In other words, it's an increasing concave down function. So the second derivative is negative. Okay? Alright. Whoops. Try another one. Let G represent the total amount of gasoline used by an automobile during a certain long trip. And we think of G as being a function of time, where, say, T hours. Okay, what is meant by G prime of T? What is its sign? And what are its units? See if you can figure that one out. Press pause. Okay. So, first of all, let's just think about the units, and that may help us. T is measured in hours. G is measured in gallons. So this is gallons per hour. Well, if this is a trip, as long as they're actually moving on the trip, G prime of T should be, G of T is increasing. The longer time goes along, the more gasoline they're going to use. Now, if they're at a point in the trip where they're stopped and the car's turned off, then they're actually going to, the sign will be 0, so the because the G is constant, it's not increasing. But G would definitely not be negative. The only way you're not going to, a car doesn't generate gasoline as it travels, it burns gasoline. And the units then would be the units of G per T, so gallons per hour. Okay. I'll tell you what, let's stop the video here and we'll look at some more in the next video.